Hello, good morning to everyone. Myself, Professor Prashantu Chatterjee. I am going to teach system of ordinary differential equations. Before teaching system of ordinary differential equation, I want to say something about the eigenvalues and eigenvectors of a square matrix. What is an eigenvalue and what is an eigenvector? Eigenvalue is a number, either real or complex, but not equal to 0. So eigenvalue is a non-zero number, real or complex. Eigenvector is also the corresponding vector, is a vector, which is, this is also non-zero vector, but it should satisfy the relation Ax equal to lambda x, where A is the square matrix, lambda is the eigenvalue, and x is the eigenvector. So example, suppose A is a matrix 6 minus 3 2 1. Then if we consider this particular equation 6 minus 3 2 1 into the vector 3 2, that is A into x equal to 4 into 3 2. As this particular equation is satisfied by both 4 and 3 2, so 4 is called the eigenvalue and the vector 3 2 is called the eigenvector. So how to find eigenvector? Suppose A is a n by n square matrix. Then if we take the determinant of A minus lambda I equal to 0, this determinant gives you a polynomial of degree n of lambda. To solve the roots of this polynomial are n numbers, and these n numbers are called the n eigenvalues. So what may happen? There are several cases may happen. Suppose lambda 1, lambda 2, so on to lambda n are n distinct eigenvalues of the matrix A, then corresponding to every eigenvalue lambda 1, we should get an eigenvector x1. For lambda 2, we get an eigenvector x2, so on to for lambda n, we get eigenvector of xn. As all these eigenvalues are distinct, so all these eigenvectors x1, x2, so on to xn form a set of n linearly independent vectors. So x1, x2, so on to xn are linearly independent. কিন্তু এটা হতে পারে, it may happen that A is a n by n square matrix and all the eigenvalues are not distinct, so some are repeated. Suppose an eigenvector of multiplicity m, where m lies between 1 to n, then the repeated characteristics value having multiplicity m has p linearly independent characteristic vector corresponding to it, where p lies between 1 and m. If n by n matrix A has one or more repeated characteristics values, then there may exist less than n linearly independent vectors. Example, suppose A is a matrix 1, 2, 3, 4. If we do in this way, if we find the determinant value of A minus lambda I equal to 0, it will give a polynomial of lambda, and solving this polynomial, one can easily find that lambda equal to 4 and lambda equal to minus 1 are two eigenvalues of this matrix A. Now we want to find out the eigenvector corresponding to these two eigenvalues, lambda equal to 4 and lambda equal to minus 1. Suppose x is the eigenvector. It can be written as a column vector x1, x2. So x should satisfy the equation Ax equal to lambda x, where lambda equal to 4. So putting the value A This is 1, 2, 3, 2, x, x1, x2, 4 into x1, x2. We get two equations. X, x1 plus 2x2 equal to 4x1, x1 plus 3x1 plus 2x2 equal to 4x2, which gives the relation 3x1 equal to 2x2. So if we put x1 equal to 2h and x2 equal to 3h, these two equations are satisfied. So accordingly, we can say that x equal to 2k, 3k is a vector which satisfies this equation for any value of k other than 0. So removing k, we can say that 2, 3 is the corresponding eigenvector corresponding to the eigenvalue 4. Remember that 2, 3, this eigenvector is not unique. It can be written in any form provided it satisfies this equation 3x1 equal to 2x2. Similarly, one can show that for lambda equal to -1, the eigenvector is, or the eigenvalue lambda equal to -1, the eigenvector is 1, -1. Now, I want to discuss the matrix method for homogeneous linear system with constant coefficient. So let us start with a simple case, two equation and two unknown. So a system of linear first order ordinary differential equation, if it is homogeneous, then it can be written in this way for two equation and two unknown. Suppose the first equation is dx1 d2 equal to a11 x1 plus a12 x2. Second equation is dx2 dt is equal to a21 x1 plus a22 x2. This equation can easily be written in this form: dx dt equal to capital A x, where capital A is the matrix a11 a12 a21 a22 and x is the vector x1 x2. This is why this equation is also termed as vector differential equation. How to solve this equation? So solve means you have to find the value of x, non-trivial value of x, because if x equal to 0, then automatically this equation satisfies that value. But we should find a value of x for which the equation satisfied. Since x is a vector, so we assume that alpha e to the power lambda t, alpha is be a solution of this equation dx dt equal to ax, where alpha is a vector and lambda is a scalar. Now, since x equal to, where alpha equal to alpha 1, alpha 2, x equal to x1, x2, and lambda is a scalar. So dx dt equal to lambda alpha e to the power lambda t. So putting the value of x and dx dt, that equation we got a minus lambda into alpha equal to 0. So the condition under which this particular equation a minus lambda into alpha equal to 0 gives a non-trivial value, non-trivial solution for alpha is that a minus lambda equal to 0. This is the condition. So a minus lambda equal to 0 implies we get a polynomial of lambda for which we get unknown values of lambda. So since it's a quadratic equation, we can get two roots lambda 1 and lambda 2 of the equation, which are the characteristic values or eigenvalues of the matrix A. We can find out the corresponding eigenvectors also. So if lambda 1 is the eigenvector value and alpha 1 is the eigenvector, then alpha 1 e to the power lambda 1 t is a solution. If alpha 2 is an eigenvector, lambda 2 is the corresponding eigenvalue, then alpha 2 e to the power lambda 2 is another solution. So if lambda 1, lambda 2 are real and distinct, then alpha 1 and alpha 2 should be linearly independent, and x equal to c1 alpha 1 e to the power lambda 1 t plus c2 alpha 2 e to the power lambda 2 t, and c1 and c2 are arbitrary constant, is the general solution. So if we consider this homogeneous example, if we consider this homogeneous linear equation dx1 dt equal to 6x1 minus dx2 dt equal to 2x1 plus x2, then this equation can be written in this form: dx dt equal to this 6 minus 3 2 1 x, or x is the vector x1 x2. So the solution, to obtain the solution, first we should find out the eigenvalues and eigenvectors of the matrix A. So as I discussed earlier, if we proceed in that way, it can be seen that lambda 1 equal to 3 and lambda 2 equal to 4 are two eigenvalues of A, and alpha 1 equal to 1 1 and alpha 2 equal to 3 2 are the two corresponding eigenvectors of the matrix A. So two solutions may be written as: one solution is 1 1 e to the power 3t, that is e to the power 3t e to the power 3t. Another solution 3 e to the power 40, 2 e to the power 40. So the general solution will be x equal to c1 x1 plus c2 x2, and c1 and c2 are arbitrary constant. Or the solution can be written in this form: x1 equal to c1 e to the power 3t plus 3c2 e to the power 40, x2 equal to c1 e to the power 3t plus 2c2 e to the power 40, and c1 and c2 are arbitrary constant. But it may happen that lambda 1 and lambda 2 are not distinct, they are real and equal. Then one, suppose lambda 1 equal to lambda 2 equal to lambda. The lambda is the common eigenvalue. So for lambda we get an eigenvector alpha. But we need another one eigenvector alpha. That eigenvector may be obtained by this equation: a minus lambda I into beta equal to alpha. If we get this vector beta, then two linearly independent solutions are obtained as: one is alpha e to the power lambda t, another is alpha t plus beta e to the power lambda t. Accordingly, the solution will be x equal to c1 alpha e to the power lambda t plus c2 into alpha t plus beta e to the power lambda t. This is the general solution. So suppose this is the equation: dx1 dt equal to 4x1 minus x2, dx2 dt equal to x1 plus 2x2. So the vector differential will be dx dt equal to x, where a equal to 4 minus 1 1 2 and x equal to this vector x1 x2. It can be easily shown that finding the determinant a minus lambda equal to 0, we can obtain that lambda equal to 3 is the eigenvalue, and the corresponding eigenvector is alpha equal to 1 1. So x equal to e to the power 3t e to the power 3t is a solution. Another linearly independent solution can be written as alpha t plus beta e to the power lambda t, where beta can be obtained from this equation: a minus lambda I beta equal to alpha. So just if we calculate in this way, it can be easily seen that beta equal to 1 0. So another solution, linearly independent solution, is alpha 1 1 t plus 1 0 alpha t plus beta e to the power 3t, that is t plus 1 e to the power 3t, t e to the power 3t. So the general solution can be written as in this way: x equal to c1 e to the power 3t to the power 3t plus c2 t plus 1 e to the power 3t plus and t e to the power 3t. So the general solution may be written in this form: x1 equal to this c1 e to the power 3t plus c2 t plus 1 e to the power 3t, x2 equal to c1 e to the power 3t plus c2 t e to the power 3t, and c1 c2 are arbitrary constant. Sometime it may happen that the eigenvalues are not real, they are complex conjugate. Suppose we consider this particular example: x1 x dot equal to x minus 5y, y dot equal to x minus 3y, with the initial content x0 equal to 1, y0 equal to 1. So eigenvalues can be obtained by doing the determinant a minus lambda equal to 0, which gives the value of lambda equal to minus 1 plus minus I. So suppose we want to find out the eigenvector for the eigenvalue minus 1 plus I. So if A equal to U1 U2, then solving this particular equation, one can easily see that U1 equal to 2 plus I and E2 equal to 1. That is, E eigenvector may be written this one 2 1 plus I into 1 0. So if we consider the another eigenvalue minus 1 minus I, then naturally 2 1 minus I 1 0 will be the eigenvector. Putting this value, one can easily obtain that two solutions may be written in this form: e to the power minus t 2 1 cos t minus 1 0 sin t, e to the power minus t 2 1 sin t plus 1 0 cos t. So now at t tends to infinity minus t tends to 0, so the solution is stable. Please do the exercise 1, 2, 3. Thank you for listening my lecture.